Benjamin Franklin once said that in this world nothing can be said to be certain except death and taxes. Now, if I could humbly add one more to this list, it would be waiting in line. No matter where you go or what you do, lines are inevitable. But as much as I hate waiting in lines, I do want to share with you a fascinating type of mathematics I've learned recently that can make waiting in lines just a little bit more bearable. The mathematics I'm talking about is queuing theory. Queuing theory can be applied anywhere and anytime you are waiting in line, and I hope this video helps you become a bit more familiar with this fascinating and useful topic. In this video, I will be walking through three questions. What is queuing theory? What is Little's Law, which is a fundamental principle of queuing theory? And finally, how to apply queuing theory. Queuing theory is the study of, unsurprisingly, queuing systems. You can think of a queuing system as a box that people, objects, or jobs enter, wait for a period of time, receive a service, and then exit. If we look inside a queuing system, we can find two major components. The first is a queue, which you can think of as a waiting room. Once a customer enters, they wait here until they can be served. This brings us to the second major component, the servers. The servers help the customer with some task, and then the customer leaves and is replaced by the next person in line. Note that the size of the queue and the number of servers can vary depending on what you are trying to model. Once your queuing system has been defined, you can begin to evaluate the system using mathematics. I want you to think for a moment the last time you were in a long line, and try to come up with some questions that you can ask about the line you are waiting in. Here are three common questions you can ask about a queuing system. How many people are in the line on average? How long does it take to get through the line on average? And how often is the system busy versus idle? It doesn't take much to realize that the answers to these questions are extremely useful. Unfortunately, the answers can vary dramatically depending on the type of queuing system. Fortunately, there is one fundamental principle that applies to nearly every queuing system out there. This brings us to Little's Law. This law revolves around the all-important question we all ask ourselves. Why is this line taking so long? Think about the last time you went grocery shopping. When deciding which checkout lane to go into, what factors were you considering at the time? Little's Law addresses two of the most important ones. First, it recognizes the longer the line, the longer the wait. And second, the slower the line, the longer the wait. Our first guess at this relationship, then, is the line length divided by the line speed equals wait time. With a simple rearrangement, you may notice this equation has a striking similarity to the well-known formula, distance equals rate times time. This similarity is no coincidence. Let's take a deeper look at each variable. First, the distance in a queuing system can be thought of as the average length of the line. Instead of dealing with kilometers or miles, we are dealing with how many spaces we need to move in order to get to the end of the line. Do note that Little's Law is a bit broader as it considers all people in a queuing system, but for now, thinking of the length of the line is good enough. Time is a straightforward comparison. The wait time in a queuing system is simply how long it takes a customer to go through a queuing system on average. And finally, the rate or speed is a bit trickier than the other two, because Little's Law uses the arrival rate of new customers. Let's take a moment and see why this is the same as the speed of the line as a whole. We first must recognize that Little's Law makes two assumptions. First, the constants are consistent. That is, you can't use hours and seconds at the same time. And second, the system is stable, meaning that the length of the line, arrival rate, and wait time are not skyrocketing to infinity or plummeting to zero. Let's quickly add a new variable, the departure rate of customers from the queuing system. Based on our assumptions, we can easily demonstrate that the arrival rate must be equal to the departure rate. If we assume the arrival rate is greater than the departure rate, then the length of the line will increase to infinity. But if we assume the arrival rate is slower than the departure rate, then the length of the line will drop to zero. Therefore, the arrival rate must equal the departure rate. Consider for a moment what the departure rate means. If you are waiting in line, then every time someone leaves the line, you move forward one space. To summarize, the arrival rate is the departure rate is the rate at which you move forward in line. Thus, the arrival rate represents the speed by which you are moving through the line. Now we can summarize Little's law. If I want to calculate the distance traveled in a line, that is the length of the line, all I need to do is multiply the speed by which I'm moving through the line by the amount of time I spent in the line. Or in other words, distance equals rate times time. We can also use Little's law to estimate how long it's going to take to go through a line. You simply take the average number of people in a queuing system and divide it by the rate of arrival of new customers. Let's suppose you're at the DMV and there are 50 people in line and a new person arrives every 5 minutes. Little's law says you should get comfortable because you have about 4 hours of waiting ahead of you. In this final portion, I want to explore two applications of queuing theory that use Little's law. First, imagine you are working the front desk by yourself, and you want to know what percentage of the time you are working. Then, like any other normal human being, you realize that you are a queuing system of size 1. That is, a customer walks up, you help them with some task, and then they leave. The number of people in your queuing system at any specific moment can only be 0 or 1, as you can only help one person or group at a time. Therefore, the average number of people in your queuing system will be some number between 0 and 1. Let's suppose that the rate of arrival of new customers is 1 customer for every 5 minutes, and that you spend on average 1 minute helping a customer. Multiplying the two together gives us 0.2 persons. Remember, this number means that out of every 5 minutes, you are spending 1 minute helping someone, or in other words, you are busy 20% of the time. This application on how busy a server is has become so important that it has its own name, the utilization law. Remember, though, that this law is simply Little's law applied to an individual server. For our second application, imagine you are at an event, but before you can enter, you need to check in with your smartphone. If you are running the event, then you might want to know how many people are standing around filling out the check-in on their phones at any given time. But because this is a queuing system, you can use Little's law to answer this question. And the variable you are trying to find is the expected number of people in your queuing system. So, let's assume that the rate at which new customers are arriving is 2 per minute, and the average amount of time it takes to check in is 2 minutes. Multiplying these two together, Little's law states you can expect to see 4 people checking in at any given time. If these examples are intriguing to you, I encourage you to look more into queuing theory. Here are 3 concepts worth exploring. First is Kendall's notation, because it is the language used to describe queuing systems. Second are Markov chains, because they describe how a system evolves over time. And third, Poisson processes, because they can model, amongst many other things, how customers arrive randomly into a queuing system. Thank you so much for watching this video, and I hope it makes waiting in line just a little bit more interesting. I also want to thank 3 Blue 1 Brown for putting on this Summer of Math Exposition.